Okay, so we're going to start the acids and bases chapter. This is 14.1, the definitions of acids and bases, but we're going to skip around a little bit in the chapter. I'm also going to avoid titrations because we're going to cover that in the end, and I'll probably cover that in class some because it makes sense to cover that in class, especially because we're going to be doing a handful of labs on that, at least I hope. So, and then I am going to kind of intermingle these ideas. So there's some parts that are not going to necessarily line up with any of the sections in the OpenStax book, but we will we'll try our best. But you'll have all the content by the time you finish, so you'll understand all of this, I hope. So acids and bases. So acids and bases are incredibly important in chemistry. And we have a handful of different definitions that are going to help us define what an acid and a base is. So we always start with the Arrhenius definition. It's the earliest definition, and this is what is stated as. So an acid is a substance that. So an acid is a substance that when dissolved in water, and that's an important part because it's dissolved in water. None of these, the other two definitions that we have do not involve any solvent whatsoever. So acid is when dissolved in water, increases the concentration of H+, that hydrogen ion. So increases in concentration of H+. That is the definition of an acid according to the Arrhenius definition. Base, on the other hand, is a substance that when dissolved in water increases, again, water increases the concentration of OH-. So increases the concentration of OH-. So we see an increase in that. So again, any substance that you add to water and increases H+ is considered an acid. Anything that you add to water that increases OH- is considered a base. So it's a pretty broad definition, but not quite enough because it's labeling a solvent. So the broader definition came from Bronsted-Lowry, and this is the one that we use outside of organic chemistry. Organic chemists use a Lewis definition, which we're going to kind of skip. I'll talk about it at some point, but not right now. So Bronsted-Lowry is the definition that we're going to use most in our conversation. So Bronsted-Lowry acid. So instead of focusing on the production of H+ or OH- in solution, we're going to look at one simple thing, which is the H+. So it's going to view H+ as major player, major focus, I should say. So we're going to view H+ as kind of our major focus. So the Bronsted-Lowry acid is defined as any substance that is a proton or H+, which is just a proton because it's missing its electron donor. So anything that donates a proton or anything that gives up a proton is going to be considered a Bronsted-Lowry acid. As an example, and this is my example, if I had something like hydrochloric acid, it becomes H+ and Cl- aqueous. So all of those are aqueous. So that Cl- has essentially donated the H+ or given it to the solution to go and react somewhere. So it's by definition, it's going to be a Bronsted acid. So the Bronsted base is a proton H+ again, acceptor. So we're looking at the exchange of an H+. So the same kind of idea, if I have, for example, OH-, if it combines together with H+ to give me water, the OH- has accepted the H+. In this case, the first case, we're looking at the chloride. The chloride has getting rid of the H+. So that H+ is kind of the free unit to go wherever it likes. So there's a little bit of a problem with the definition of a hydrogen ion. A hydrogen ion is literally just one, if you think about it, we've lost an electron and it only had one electron to begin with. So it had one proton. That's just a proton just cruising around in solution. That really cannot exist in solution. We don't have just random protons that are cruising around. So this cannot exist in solution. So there's a problem here, because if that can't exist, how can we represent it? It's more proper to actually represent it or to recognize it, because this is actually what it looks like in solution, more proper to use the hydronium ion. The hydronium ion is H3O plus, or it's basically water acting as a base and taking on an H plus to give me H3O plus. So the other way to kind of see it in yeah, there we go. That whole thing is positively charged. It is the hydrogen that has been accepted. So if that's my H plus, one of these is going to, this is more properly known as the hydronium ion. So either of those, hydronium. So we are still going to use the term H plus, but when you use H plus, it is essentially the same thing as writing H3O plus. We just kind of assume that although H plus is there, there's a water included. So for example, a acid reaction showing the water would be HCl plus water, because you cannot have an acid without a base. You cannot have an acid reaction without a base. Here I have water aqueous, or sorry, HCl aqueous with water. This actually produces H3O, the hydronium ion, plus Cl minus, which is still in solution. So that's showing the water molecule. This is the more proper way to write it, but just because we're chemists and we generally don't, I mean, we literally get rid of an E on the end of mole. So just to make things simpler, we write it out as H plus aqueous plus Cl minus aqueous. But we full well know that this is in fact H3O plus. As chemists, we know that it's there. We know that this reaction actually included H2O, but we don't write it. And my dog is chewing something, so one moment. And she is no longer chewing it. Okay, here we go. So that's the idea behind the definition of an acid and a base, the donation of a proton. So we're pretty much going to look at the Bronsted-Lowry definition. We're going to ignore the the other one is there. The Arrhenius solution, the definition is there, but generally it's better just think that it was Bronsted-Lowry. So proton donation versus proton exception. We have these things that are amphiprotic and amphiprotic molecules. So right now we've said, all right, they can be an acid or they can be a base. Well, it turns out that we can have something that's amphiprotic, which is a molecule or an ion, which can act as either an acid or a base. So by definition, a molecule or ion that can be an acid or base. It can do both. Okay, so acid or I guess I should say, and or base. So it can actually do both of these things. So if we take a look at water as kind of the prime example, if it acts as an acid, that means it's going to donate the H plus. It's going to get rid of the H plus. And so what we end up with is acting as an acid, you have H plus plus OH minus. So I'm just going to highlight. So water acting as an acid turns into OH minus, okay, because it acted as an acid. On the other hand, if it acts as a base, acts as base, where it's going to accept an H plus. Again, we don't really need to know where the H plus is from, but H plus, so we're just going to say acts as a base means that I'm going to include, there's H plus somewhere to be had. It becomes H3O plus aqueous, and there we go, it acting as a base. This is setting something up. So the idea is I start with water. If it can act as an acid, it can donate that H plus and become OH minus, or it can accept an H plus and become H3O plus. So we kind of have both of those things that can occur in the same thing. How about H2PO4 minus? This is amphiprotic as well. So what does it look like when it acts as an acid? When it acts as a base? As base, as acid. So pause this and give this a go. So if it acts as an acid, it becomes, that means it's donating the H plus. H2 becomes HPO4 and H plus. So I have the H plus. We have gotten rid of a positive charge. That means the charge is going to drop by 1. If it acts as a base, again, we are adding a proton to it, and it becomes H3PO4. Although it doesn't feel balanced, keep in mind that this is included in the reaction as well. So we have that as well. So this all brings about the idea of what happens when an acid is dissolved in water. What happens, we get this thing called conjugate acid and base pairs. So we have conjugate base and hydronium ion are going to form. We're going to have these what we call conjugate acid-base terms or acid-base pairs. So if we start with HCl dissolving in water, so aqueous HCl in liquid water is going to yield Cl minus, because again, if this is acting as an acid, that means that the water here is going to be acting as a base, meaning the Cl minus, the HCl is going to be donating because that's what an acid does, and the base is going to be accepting. So plus H3O plus, and both of these are aqueous. So if we take a look at this, what we see is the HCl is paired up with the Cl minus. It has donated H plus. The H2O, on the other hand, has accepted that H plus. Okay, great, all done, right? So we have to recognize that we are now in an equilibrium situation. We could also go in the reverse direction. So if we go in the reverse direction, what we see is this chloride now turns into HCl. So it has taken one of these H pluses and gained it, and now it becomes HCl. So this Cl minus is now accepting a proton. So this is now acting as a base. But what we're going to call this is a conjugate base. So an acid now has a conjugate base pair. So HCl is the acid, the conjugate base is Cl minus. Much like up here, H2O, if it's an acid, its conjugate is OH minus. Okay, so the conjugate, what you'll notice is if you have an acid, actually, I'll just point it out. If I have an acid, the conjugate is missing an H plus. Much like if I have a base, its conjugate has gained an H plus. So on the other side of this, if H2O is a base, H3O is going to be the conjugate acid. These are what we call conjugate acid-base pairs. These are going to be important, really important when we start to look at buffers. So these are known as conjugate acid-base pairs. So the term conjugate comes from Latin, to join together. Reactions between acids and bases always yield their conjugate acid-base pairs. So with that said, if I have HNO2 reacting with water, it's in some kind of equilibrium. We don't need to know anything other than it's in equilibrium, NO2 minus and H3O plus. What are the conjugate acid-base pairs that we have here? So pause this and write out which one's acid, which one acts as an acid, which one is the base, and then do the same thing for the products, and then we're going to pair them up. Okay. HNO2 becomes NO2 minus. We always kind of put the anions together. So we know that this is acting as an acid, and therefore the NO2 minus is the other portion of it, is the conjugate base. That means that H2O, excuse me, is acting as the base, and we see H3O as the conjugate acid. And let's take a look. So Going in this direction, we notice that it does act as an acid because it donates the H+. These two things together are conjugate acid-base pairs. HNO2 and NO2- are conjugate pairs. Versus H2O paired up with H3O+, these two are considered conjugate acid-base pairs. Again, gaining a proton, the other one loses a proton. Or one has a proton, the other one loses it, and vice versa. Okay, so conjugate acid-base pairs are important. The reason that we have to understand these conjugate acid-base pairs is because relative strength is tied to this idea of conjugate acid-base pairing. So understand this, and that's the end of the definitions. We're going to talk about relative strengths of these things. This chart is really important for being able to understand buffers, being able to understand strengths of acids. So have one of these handy if you can, or at least make sure you have this printed out so you can have this handy when you're doing this next thing.